Vectors have direction and magnitude. That means they are a directed line segment or array. Not array, because array we go on forever, but they're a line segment that has a direction. It has an arrow. Now, to be equivalent, vectors would have to have the same magnitude, the same length, and the same direction. Well, the direction would be the slope of that point. So we have these two vectors. Golly, I can learn to talk. U goes from 0, 0 and ends at 3, 2. And V is going from 1, 2 and ending at 4, 4. So the initial point is where it starts, terminal point is where it ends. If we wanted to show that these two were equivalent, I have to show two things. I have to show that they have the same direction and the same magnitude. So direction would be the slope. So slope of U would be up to right 3. So 2/3. And the slope of V would be up to right 3. So they have the same slope, but that doesn't automatically mean they have the same length. So to find the length, we can use the distance formula or the Pythagorean theorem, because it's the same thing. So if I wanted to find the length of U, and the way we denote that is with this double bars. That means the length of U. I'm going to use the distance formula. Well, actually, let's just draw since we got the picture. Okay. It's going to be the square root of this length squared, so 3 squared, and then the height here, which is 2 squared. That's 9 plus 4, so that's the square root of 13. The length of V. The horizontal distance is 3, and the height is 2. So they are equivalent. There's another way to write a vector, and it's called the component form. The component form is written as the change in the x's, comma, the change in the y's. Which means you already have your horizontal distance and your vertical distance, the change in your x's, change in your y's. So it actually helps when you're finding the magnitude. So on this example, we're going to write it in component form and then find the magnitude. So to write it in component form, I'm going to call that, goes from P to Q. Okay, so P to Q is going to be written as, so a vector is written like this with pointy parentheses. It's going to be x2, so the ending x value minus, ending x value minus the beginning x value. So the order actually does matter here. Ending minus beginning. Ending y value minus the beginning y value. So the other way to think about this is to get from point here to point here, I have to go left 5, and that's 12, and then up 12. Left 5, up 12 goes from the initial point to the ending point. Now the magnitude of that would be the square root of the change in the x's, which is -5, squared, plus the change in the y's, squared. That's 25 plus 144. It's the square root of 169, which is 13. Vector operations. So here's two vectors written in component form. What do you think it means to find 2v? Well, it's going to be twice as long. So it's 2 times each of the components. What do you think it means to do w minus v? Well, that would mean I'm taking w minus v. Think about it. 3 minus a -2, and then 4 minus 5. V plus twice w. So twice w would be 6, 8, because 3, 4, twice that is 6, 8. And if I'm adding those together, I'm going to add the components. And done. The next topic is unit vectors. Unit vectors are vectors with a magnitude of 1. That puts them into our lovely little unit circle world where everything is 1 long. So if we have a vector, and here's its component form, that means it's left 2, up 5, and we wanted to find the unit vector that matches that. So what we're doing is, okay, so let's say this one is going left 2, 1, 2, 3, 4, 5. This would be an equivalent vector that's got the same component. What we're wanting to do is shorten that to only be 1 unit long. So shorten it. The way we're going to do that is we're going to take the vector and divide the vector by its magnitude. So I'm going to come over to the side and find the magnitude of v, which is going to be my horizontal distance squared plus my vertical distance squared. That's 4 plus 25 square root of 29. So in other words, I'm going to take each of the components and divide it by the length of the original vector. Now this is perfectly correct, but I'm not sure if the software lets you leave it like that. If it doesn't, then all you would have to do is change that to a square root of 29 on the top and 29 on the bottom, and square root of 29 on top, 29 on bottom. We can also write unit vectors using what is called linear combination. So writing it as a linear combination. And I know it's weird it says using unit vectors I and j. All it means is I'm going to rewrite this. So u was 2, -5. I'm going to rewrite that as 2i and -5j. Oh, whoops. I can't do that. Oh my goodness, I first have to find my component form. Oh, that's what I did wrong. My component form, my vector, is going to be the terminal minus the initial. So x minus x, so -1 minus 2, and then 3 minus a -5. I first have to find that. Oh my goodness, I was having a brain damage moment. So my horizontal distance and my vertical distance. Now I can write it as a linear combination. So what if we had two vectors written in their linear combination form, and I was asked to find 2u minus 3v? It makes the operations a little bit easier because 2u minus 3v means I'm going to do exactly what you would think you would do. Distribute, and then combine like terms. Direction angles. So we can talk about the direction in terms of slope, but we can also actually find the angle that gives us this direction, gives me this vector. So I've got vector u already drawn out, and it's 3i, 3j. That just means it went right 3, up 3. This side is a 3, this side is 3. How would I find the angle right there? Tangent equals opposite over adjacent. And that actually ends up being 45 degrees, or pi over 4. Let's do another one. This one is 3, -4. So that means it's going this way 3, and then, oops, I'm sorry, this way 3, and then down 4. Oh my goodness. So the direction angle is going to be my change in y's over my change in x's. Oh, it's the slope. Now this one I don't know off the top of my head, so I would do inverse tan of -4/3. And I'm going to put mine in degrees. Depending on, make sure you read the problem, whether it asks for the answer in degrees or radians, and how many decimal places it wants. Okay. Ooh. This is kind of crazy. Don't look at that right now. I want you to look at this picture. Find the component form of the vector. So that means we want the horizontal distance and vertical distance that represents the velocity of an airplane descending at a speed of 100 miles per hour. So the magnitude is 100. and it's 30 degrees below the horizontal. So that means my reference angle here is 30 degrees. How would I find this horizontal distance here? I'm going to call it V1. I'm going to call the vertical distance V2. Let's think about how I would find those distances. Well, that's adjacent, and I know the hypotenuse. So cosine of the angle would equal V1 over that distance. In other words, that magnitude times cosine is going to give me my horizontal distance. The magnitude times the cosine of the angle gives you your horizontal distance. To find the vertical distance, we would have to use sine. And lo and behold, it's going to be the magnitude times the sine of the angle. So 100 times the cosine of 30 and 100 times the sine of 30. But it's not, ooh, you know what? I don't really want that 30. I want the entire angle. What is that entire angle? It's not 30 degrees. That's just the reference angle. Well, that's 180 plus 30. That's actually 210. And I could look back at my chart and look at 210, and cosine would be the x value. And sine would be the y value. You could also put it in your calculator. So this is going to be 50 times negative square root of 3, so that's negative 50 root 3. And this would be negative 50. So I could write vector v as the horizontal component and the vertical component, or write it with the weird I's and the weird J's, but it's still the same thing.